Hi and welcome to another episode from Spiral Physics Education. It's going to be looking at the volts in this episode, also a bit about electromotive force or e.m.f, and also PD or potential difference, and also about how the voltmeter is used to measure potential difference. We're looking at the equation voltage is work done per unit charge, and also about the rules of voltage and potential difference in series circuits and also in parallel circuits. So to get the most out of this lesson, what you really need to know is that charge is measured in coulombs, and that 1 coulomb is made up of a certain number of electrons. The 6.25 times 10 to the 18 electrons, that you don't need to know that, but just be aware of there is a fixed number of electrons that make up 1 coulomb of charge. Also need to know what a series circuit looks like, what a parallel circuit looks like, and the current rules for series and parallel circuits. So looking at the volts, so this is a general definition. Volt is work done per unit charge. And to remind you about what work is, well, work is measured in joules and it's about energy, and unit charge is a fancy word for saying 1 coulomb. And if you remember 1 coulomb, I want you to visualise 1 coulomb as a cloud containing 6.25 times 10 to 18 electrons, or a fixed number of electrons. So if we think about that and break down what 1 volt means, 1 volt means 1 joule per coulomb. So we've got our visual aid, we've got our 1 joule of energy, so that's the lightning, and it's linked to this 1 coulomb, this cloud. And if we think about 2 volts, well, that's 2 joules per coulomb. So we've still got the same coulomb, but it's just got more electrical energy associated with it. And if we went all the way up to 240 volts, which is 240 joules per coulomb, it's the same coulomb of charge, but it's got even more electrical energy. And that means it can do more work. It can go around a circuit, and that's 240 joules of electrical energy can be transferred into other forms of energy and useful energy. So let's have a look at e.m.f or electromotive force. But don't get confused by that. It's not really a force. It's still measured in volts, but it's specifically for power supplies. This really isn't that appropriate for GCSE or IGCSE level, but certainly if you wanted to go into AS or A level in a bit more detail, having an idea about e.m.f is a good idea. So the definition of e.m.f is very similar to the volts, but it's the work done per coulomb of charge in converting chemical energy store into electrical energy transfer. So what that means is that if you have a 1.5 volt battery, that means that when that battery delivers a coulomb of charge around a circuit, 1.5 joules of its chemical energy is turned into electrical energy. So each coulomb that flows out of that battery will have 1.5 joules of electrical energy, and it's come from the chemical store inside that battery. So a 1.5 volt battery means that the e.m.f of that battery is 1.5 volts, and that means it can deliver 1.5 volts or joules per coulomb. Okay, so potential difference. So potential difference is also measured in volts, and it's slightly different from electromotive force and a little bit more detailed than just the volt. But again, it's a term, potential difference or PD, is used a great deal at GCSE, but you need to know more about it at A level. So it's more of a helpful idea about the vocabulary used at GCSE. So when we say potential difference, what we actually mean is it's the work done per unit charge in converting the electrical energy into other forms of energy, depending on what's in the circuit. So give you an example of that. Let's say we've got a 240 volt light bulb. That means that light bulb, when a coulomb flows through it, will do 240 joules for every coulomb that flows through it. And as that coulomb approaches the light bulb, that coulomb will have 240 joules of electrical energy. And when that coulomb gets to the light bulb, that 240 joules of electrical energy will be converted into a mixture of light energy and thermal energy. so it will do work at that point. So that's what potential difference means. And we're going to be looking at potential difference through a great deal of the examples in this video. Just to remind you, that's what a Coulomb is looking like, that little cloud. So let's have a look at a very basic series circuit. So we've got a series circuit, and it's a 1.5 joule volts power supply, which means when a Coulomb pops out of it, just like here, that 1 Coulomb has got 1.5 joules of electrical energy, and it will move around to this point here. It hasn't done any work just yet, this Coulomb, because it hasn't gone through anything with resistance. There's only this little resistor here, and this resistor is going to do all the work. When the Coulomb goes through that resistor, after it's done all of its work, then it's going to have no joules, no electrical energy afterwards. That doesn't mean no kinetic energy, it means it's got no electrical energy. And what a voltmeter does, a voltmeter goes in parallel across the device that you're interested in. So we're interested in this voltmeter, so we put a voltmeter before and after the voltmeter, before and after the resistor. So the voltmeter will look at the energy of the Coulomb before the resistor, and it will look at the energy after the resistor, and it will tell us the difference in energy, or the potential difference. So before the resistor, that Coulomb's got 1.5 joules, and after the resistor, it's got no joules of electrical energy. So the potential difference is 1.5 joules per Coulomb, or 1.5 volts. So the voltmeter will read 1.5 volts. Let's make it a little bit harder. Let's put two resistors of equal value in series next to each other. And because they're equal value of resistors, both of them got the value of R, that means they will do the same amount of work. So here we have a Coulomb, and this time we're looking at a 9-volt battery. And that 9-volt battery means that that Coulomb's got 9 joules of electrical energy, and it's going to do 9 joules of work to that circuit. These two resistors will do half of the work each. So when that Coulomb gets around to this point, hasn't done any work yet, it's still got 9 joules of energy, of electrical energy. And then after those two resistors, that Coulomb will have no electrical energy. Remember, that doesn't mean no kinetic energy, it means no electrical energy. So if each of them are going to do half the amount of work, when the Coulomb goes through the first resistor, it's done half its work. That means it's lost or converted half of its energy. So it's got 4.5 joules of electrical energy. And if we put a voltmeter across there, it's going to look at the difference in energy between those 2 points. At the first point, it's got 9 joules of electrical energy. At the second point, 4.5 joules of electrical energy. So the potential difference is 4.5 joules per Coulomb, or 4.5 volts. Put a voltmeter here, it's going to do the same thing and compare the energies at the 2 points for the between the resistor. At the first point, it's got 4.5 joules of electrical energy. At the second point, no joules of electrical energy. So the potential difference is 4.5 joules per Coulomb, or 4.5 volts. Put in a third voltmeter at the extremes, looking at one point, it's got 9 joules, looking at the other point, 0 joules. The potential difference is 9 joules per Coulomb, 9 volts. So let's have a look at a slightly more complicated circuit. Still two resistors in series, but one resistor has got twice the resistance of the other. And that means the 2R resistor will do twice the amount of work. So you've got to think a little bit in ratios here. We've got a resistance of 2 to 1. And that means that the 2R resistor will do twice the amount of work. So it's still a 9-volt battery, and we've got a Coulomb here, and that Coulomb then is going to have 9 joules of electrical energy. And these two resistors will do all of that 9 joules of work on that Coulomb. So when that Coulomb gets around to this position here, it's still got 9 joules of energy, of electrical energy. And when it gets to this point here, after those two resistors, it's going to have no joules of electrical energy. But it'll have to do twice the amount of work through that first resistor than that second one. So if it does twice the amount of work, that means that it's going to have 3 joules of electrical energy. We put a voltmeter across there. The difference between 9 and 3 is 6 volts. And if we look at the second point, the difference between those 2 points, between 3 and 0, is 3 volts. And then if we put a third voltmeter in there between the 9 volt position and the 0 volt position, the difference in potential there is 9 volts. So let's have a look at a parallel circuit. So we've got a parallel circuit and each resistor is the same value, so it'll do the same amount of work. And then we've got a 9 volt battery again, so each of these coulombs here has got 9 joules of electrical energy. So they haven't done any work just yet. At these points here, both of these coulombs have got 9 joules of electrical energy. When they go through their associated resistor on their loop, they're going to have no joules of electrical energy. And we look at the potential difference, that means it's 9 volts. And for the next one, when it goes through there, that's also going to be 9 volts. The potential difference there is also 9 volts. So if we look at the equation that we're going to look at here, it's going to be linked to the definition. So that's work done per unit charge. And that means we've got an equation of work over charge, or W over Q. So if we look at this question here, we can see that we've got a 1.5 volt battery, 5 coulombs of charge. I'm going to work out how much work is done by the power supply. So there's our equation. Those are our symbols. We're going to rearrange it so that we've got W equals VQ. And that means we've got 1.5 times 5 for our answer. So let's have a look at something else. We've got a resistor as a PD of 3 volts. I'm going to calculate the charge that passes through it if 500 millijoules of work is done. Remember, we need to convert the millijoules though. So we do that by dividing by 1000. We've got our equation, V equals W over Q. Rearrange that for Q equals W over V. And we have 0.5 over 3. And we can convert that into our answer there. So I hope that you found this introduction to voltage and potential difference useful. Don't forget to subscribe to the channel for other useful videos on physics, and hopefully they will get your understanding up so that your grades will improve. And we'll see you next time on Spiral Physics Education. Goodbye.